In this video, we will discuss round-robin scheduling algorithm. The round-robin scheduling algorithm is similar to first-come, first-served scheduling, but here the preemption is added, and each process is assigned a fixed time slice or time quantum. A time quantum or a time slice can be any length, but typically anywhere between 10 to 100 milliseconds. The ready queue is implemented as a circular first in, first out queue. The new process are appended to the tail of this ready queue. A timer is set to interrupt after one time quantum or one time slice. The current running process is interrupted. The next process in the ready queue is selected and is dispatched to run on the CPU. In the round-robin scheduling algorithm, the running process can be interrupted. So the round-robin is preemptive scheduling. In the round-robin scheduling algorithm, if the current running process has a CPU burst duration of less than one time quantum, the process voluntarily releases the CPU, and the next process in the ready queue is dispatched to run on the CPU. This means the current running process can complete within one time quantum. So the process changes the state from running to terminate. The process releases the CPU voluntarily. The next process in the ready queue will be dispatched to run on the CPU. If the CPU burst of the current running process is longer than one time quantum, the timer causes an interrupt to operating system. This means current running process cannot complete within one time quantum. The current running process is preempted or interrupted by this timer after one time quantum. And this process is appended to the tail of the ready queue. The process changes the state from running to ready because the process is interrupted or is preempted before the process terminates. The scheduler will select the next process in the ready queue, and this process is dispatched to run the CPU. And now let's take a look at an example of round-robin scheduling. Here we use the same data, 5 processes, and arrival time, CPU burst time. Same to the data we used in the first come, first served, and the shortest job first, and the shortest remaining time first scheduling algorithm. Here the time quantum or time slice duration is 2 time units. Now let's take a look at the execution order of these 5 processes. At time 0, process A arrives at the ready queue. Process A is the only process in the system, so process A is selected, dispatched to run on the CPU. Process A is running. Now, after one time slice or one time quantum, A is still the only one process in the system. So the next time quantum, the process A is still running. Okay. Now at time 4, process B arrives at the ready queue. Now process B is in the ready queue. Process A already complete one time quantum or one time slice. Process A is interrupted. Process A is appended to the tail of the ready queue. Now the process B is selected from the ready queue. This is a first in, first out queue. Now at time 4, process A is waiting and process B is running on the CPU. Now at time 5, process C arrives at the ready queue. C is appended at the tail of the queue. Now at the time 5, A is waiting, B is running, and C is waiting. Now at time 6, the process B is interrupted by the timer. So process B is added to the tail of this queue. Now the process A will be selected and dispatched to run on the CPU. Process A is running and process B is waiting, and the process C is waiting. And at time 7, A is running, B waiting, and C is waiting in the ready queue. Now at time 8, we can see this time quantum expires. The process A is interrupted by the timer. Process A is added to is appended to the tail of the queue. Process C is at the front of the queue. C is selected, dispatched to run the CPU. A is waiting, and B is waiting, and C is running. C is running. Now the C is a short process. After one time unit, C terminates. So process C terminates within one time unit or within one time quantum or the one time slice. Now the CPU is idle. The process B is at the front of the queue. B is selected to run on the CPU. B is running, and A is waiting. And also at time 9, process D arrives at the ready queue. So D is appended at the tail of the queue. So D is waiting. Now at time 10, A is waiting, and B is running, and D is waiting. Now at time 11, we can see the process B already runs on the CPU for 2 time slice. That is 4 time units. So B terminates. And now the A is at the front of the queue. A is selected and dispatched to run on the CPU. A is running, and D is waiting. Now after one time unit, we can see A already runs on the CPU for 1, 2, 3, 4, 5, 6, 7. A already run on the CPU for 7 time units in total. A terminates. A terminates, and also at time 12, process E arrives at the ready queue. Now at time 12, process E arrives at the ready queue, process A terminates. Now the CPU is idle, the process D is selected, dispatched to run the CPU. Now the process D is running and the process E is waiting. Because E is in the ready queue, E is after D. So D is dispatched to run on the CPU first. Now at time 13, process D terminates. Now E is the only process in the ready queue. E is selected. E is running on the CPU at time 13, 14, and 15. The waiting time for the process A is 1, 2, 3, 4, 5. 5 time units waiting in the ready queue. And process B, 3 time units waiting in the ready queue. And the process C, 3 time units waiting in the ready queue. Process D, 3 time units waiting in the ready queue. Process E, 1 time unit waiting in the ready queue. Turnaround time equals to CPU burst time plus waiting time. This is a 12, and this is a 7, and this is a 4. This turnaround time is 4. This turnaround time is 4. Work ratio. Work ratio equals to CPU burst time divided by turnaround time. So for process A, 7 divided by 12 is 0.58. For the process B, 4 divided by 7.57. For process C, 1 divided by 4 equals 2.25. Process D, 1 divided by 4 equal to 0.25. Process E, 3 divided by 4 equals to 0.75. Now the average waiting time is 5 plus 3 plus 3 plus 3 plus 1. This is 15 divided by 5 equal to 3. The average waiting time for the round robin is 3 time units. The average work ratio, this is 1.25 plus 0.57, 0.58. This is equal to 0.58 plus 0.57 plus 1.25 divided by 5. This is equal to 0.48. So this is a round robin scheduling example about the round robin scheduling. Here the performance of round robin scheduling depends on the size of the time quantum or the time slice. Here is an example about the time quantum duration and the number of context switches. Here we have only one process of 10 time units. That means this process, the length of CPU burst is 10 time unit. If the time quantum is 12 time unit, if the time quantum is 12 time unit, this process CPU burst length is 10 time unit, this process can complete within 1 time quantum. So there's 0 context switch. The process can complete within 1 time quantum. No context switch is needed. Now, if the time quantum is 6 time units, that means this process need 2 time quantum. In the first time quantum, running on the CPU for 6 time units, and then the next time quantum run on the CPU for 4 time units. Here we need 1 context switch. After 1 time slice or 1 time quantum, the process is switched out, change the state from running to ready. The next time the process is dispatched around the CPU, the process can run on the CPU for the next 4 time unit. Okay. This is 6, the first time quantum. And then the next time quantum running on the CPU for 4 time units. Here we need 1 context switch. Here, after 1 time quantum, the process is interrupted, change the state from running to ready. Now, if the time quantum is 1 time unit, we need 9 context switch. The process is switched is okay. Here the process. After 1 time unit, 1 time slice or time quantum, the process is put in the ready queue, and then dispatched on the CPU for another time quantum, 1 time unit, and then the switch out or the change the state to ready, and then the next time quantum. So here we need 9 context switch. Here the context switch will generate the overhead. The context switch time, just the CPU during the context switch, the CPU save the current running process information from register to process control block, and restore the new process information from the process control block back to register. It will generate overhead. So that means we don't want too many context switch. We don't want the CPU spend too much time on the context switch. If the time quantum is extremely large, that means that all the processes can complete within 1 time quantum. Now, at this time, the round-robin scheduling degenerated to first come, first serve scheduling. The performance is not good, right? If the time quantum is extremely small, the round robin can result in a large number of context switch. Just like the previous example, the time quantum is 1 time unit, and we need 9 context switch. The large number of context switches, it's not good because it wastes CPU time. Just do the context switch. So the time quantum should be large with respect to the context switch time. If the context switch time is approximately 10% of the time quantum, and then about 10% of CPU time will be spent in the context switching. This is a round-robin scheduling. In the we talked about the XV6, a very small operating system just for teaching. XV6 use a round-robin scheduling. In the XV6, it implement the scheduler function. The scheduler is implemented in the scheduler function. The scheduler loops over the process table and look for a roundable process. Roundable process means a ready process. But in the XV6, the ready process state is roundable. And the roundable process state is roundable. Once the scheduler finds a process and its state is roundable, it will switch to the process page table, the context switch to the new process, and with this function, and then mark this process as running. So change the process state from ready or from the runnable to running, and then call switch function to start running the new process. This is the XV6. Now let's take a look at the source code of XV6. Now the XV6 implement scheduler function. Each CPU calls scheduler after setting itself up. The scheduler never returns, it loops. And the scheduler function choose a process to run, choose a runnable process to run, and switch to start running that selected process. Eventually, that the process transfer control will switch back to the scheduler. This is the scheduler function. The for loop, there's no condition, for loop condition. So the for loop will never return. The scheduler never return. The for loop, there's no condition. The for loop will repeat again and again. Now inside this for loop, we have another for loop to find the runnable process. All the process are stored in the process table prog this array. Maximally, we can have 46 processes in the XV6. Now, if the process state is not runnable and continue. Continue means we'll skip this statement and go back to the loop condition. Now, if the scheduler find a runnable process, it will change this process state as running. Change the state from runnable to running, and switch to this process. And then also switch from scheduler to the selected process. This is a context switch function. And then when the process is interrupted by the timer, and switch back to the scheduler. Okay, this is the scheduler in XV6. XV6 use round-robin scheduling. This video will conclude here.